Hello, and today I'm looking at the fourth question on fourth of five on the MAT 2017, and I think this is a little bit harder than the second and third questions. So we seem to have got some kind of situation where a horse is tied up in a field, and we have to find the length of the rope if the area of its quarter circle can equal half of the area of the field. So, in actual fact, the first part doesn't seem too bad. Let's have a look at that first. So, as the area of the field is 1 unit squared, we can say that this quarter circle that the horse can travel in, a quarter pi r squared, has got to equal a half. That's half the area, and so it doesn't come out too long before we get r must equal the square root of 2 over pi. So that's the length of the rope that we need. Now the second part of the question is explain why the area that both can reach is the same as the area neither can reach. So now we've got two horses on opposite diagonals of this field, and we have to explain why the area between them that is shared is equal to the area that neither can reach. Well, if we know that each quarter circle has an area of a half, we know that the combined areas of these two quarter circles should equal 1. Of course, there's an overlap, and so this overlap must be equivalent to the parts of the field that can't be reached, because we know that half plus a half equals 1, and so that overlap must equal the unreachable areas. Okay, now the question starts to warm up a little bit. We're asked for an angle alpha, and they've told us the answer, so that's always helpful. And then we've got to show that the area that neither can reach is equal to that, that's on the screen at the moment. But of course, they told us in part 2 that that unreachable area is the same as the intersecting parts, the segments that are intersecting in the field. So that's what we should probably be aiming to calculate. Right, so let's get on with it. So my plan of attack for this is to use a bit of Cartesian coordinates. I'm thinking that the diagonal length obviously is going to be root 2, and so for this alpha that I've got to find, this angle alpha, I can see that I can break this up into a triangle that goes from the corner to the centre, which I'm going to call the origin, is the centre of my field. That can be, and that the total diagonal is obviously root 2. So the upper length of my triangle is going to be root 2 over 2, and we've already worked out the radius of the circle, which is going to be root 2 over pi. So I've got two sides of a triangle. All I need to work out the cosine of the angle and use the cosine rule is to find that length from the centre to a point I'm calling P. Now that is where the line y equals minus x, which is going through the centre of my field, meets the quarter circle, which I'm going to call, you can see the coordinates for x minus a half all squared plus y minus a half all squared is equal to 2 over pi. That's the radius squared. So hope you agree with that. And of course, if I find out where they meet, I can, by doing a simultaneous equation, work out that x is equal to the square root of 4 minus pi over 4 pi. Now of course this point that I'm looking for is to the right and down from the origin at the centre of the field. So my point P is going to be, which is on the line y equals minus x. It means my y coordinate is going to be the negative version of my x coordinate. And so there I've written down the point P. So the next part of my plan is to find that third length of the triangle, and then I can use the cosine rule. And so I need to find the distance between the origin, the centre of my field, and this point P that I've just calculated, and that's just a little bit of Pythagoras, and that works out at, root 4 minus pi over 2 pi, all square rooted. Alrighty. So now that I've worked out all three lengths of my triangle, it's a doddle to use the cosine rule, and I've set it up there. You can see a squared is equal to b squared plus c squared minus 2bc cosine alpha, and tidying it up, I think the algebra comes out quite nicely, and we end up with alpha does equal arc cos of root pi over 2 as they required. And now we get to the trickiest bit of this question, I think. We had to work out the area of the unreachable bits by both horses, but we know that that's equal to the overlapping sections. And what we can do is we can find the area of the sector for the triangle that we've been given, taking away the triangle that we've already calculated. So the sector area, take away the triangle area, the triangle going from the origin to point P, and of course that will give us a quarter of the overlap area. So if I times that area by 4, I should find the equivalent of the area unreachable by both horses. So I've started off straight away by trying to work out the total sector area, and I've drawn a picture of it. You'll notice that I've got two radii, root 2 over pi, both sides of my sector, and so I've just done like a radians kind of question, and I've worked out that what have I worked out? Well, I know what alpha is, so it's alpha over pi. So writing that out is arc cos of root pi over 2 over pi. So that's the total area of my sector of my circle so far. Next, I need to work out the area of my triangle, which I'm going to remove from the area of my sector. Now be careful, because the two sides of surrounding the angle that I know are not the same length anymore. Remember, this is the going to the centre, so it's root 2 over 2 and root 2 over pi. And I've used half AB sine theta. Now, of course, we've got sine alpha. I've got cosine alpha. How do I get sine alpha? Well, we know that cos squared plus sine squared equals 1. And so with a little bit of manipulation, you work out that sine alpha must equal root 4 minus pi all over 2. And so if you do the multiplications, I think you end up with the area of my triangle being root 4 minus pi all over 4 root pi. Now, of course, I've got to take that away from the area of my circle sector, okay, and then multiply that answer by 4. And if you do so, you end up nicely with the right answer, in actual fact, which they give us in the question. Okay, so a third horse is now put into the field, and the 3 horses are rearranged. And definitely you want to draw a little diagram of that when you're working away on this. Now, the specific problem we've got to work on is given that each horse can access an equal area of the field. So we're going to have well, 2 semicircles and a quarter circle, but they've got to have equal areas and nothing overlaps. So what length of rope must each horse have to minimize the area that no horse can reach? Alright, so let's go for that. So I'll concentrate first of all, as you can see in my diagram, on horse 1 and horse 2. They're not allowed to overlap, so that they can be tangential, can't they? So if I put the 2 semicircles as I position them there, and I know using my Cartesian sort of coordinates, the length it's between them directly is going to be 1 over root 2. So half of that will be the radius of the 2 semicircles, which will be 1 over 2 root 2. And because I've got the radius, I can work out the area. And of course I want my third horse to have access to an equal amount of area. So horse 1 and 2 can each reach an area of pi over 16. So horse 3 needs to have an area of pi over 16, but of course it's a quarter circle, and therefore its rope is going to be a length half, as opposed to the other horses who have a length of pi over 16. So we get to part 5, and we're told now that the 2 horses 1 and 2 are replaced by goats, and we want to know, well, obviously got a range of values, so we're probably going to think of a couple of situations, and they're saying that none of the animals' areas can overlap still, and show that, well, half of that inequality I think we've already got. but let's find the other part. So definitely want to have some diagrams for this part of the question. So my first idea was to think, well, what happens if we let the horse have a length of rope that is 1 long? Then it's going to be able to reach over half of the field. And of course that's going to restrict or make our goats space, which are not allowed to overlap.
It's 12 o'clock.
Quite small. So if you do a little bit of Pythagoras, you can work out that that would indeed be the goat would have a minimum length of rope of root 5 minus 2 over 2. Then of course if we allow the goats to go maximum length of rope, well, we can't have the goats overlapping, so we get the situation that we had in part 4. And in fact, we have already worked that out. So it is indeed the fact that G has to be smaller than 1 over 2 root 2, but larger than root 5, or equal to root 5 minus 2 over 2. And there we have it.